Circuits frequently experience a response of the source having a complicated waveform such as rectangular, pulse, square, ramp, etc. in addition to the step DC, exponential and sinusoidal signals. The signals may be recurrent type or non-recurrent type and mostly involves the passive circuits. Here we are going to discuss about the basic types of special signals commonly used. Shifted unit step function. This function remains at 0 value until t equals to a, and at t equals to a it abruptly changes from 0 to unity, and it is represented in the waveform like this: 0 and t, here let it be a, and this is unit function, so amplitude is 1. The function remains 0 until the a. At a it abruptly changes from 0 to a, and this can be expressed as u of t minus a, total t minus a, so before a it will be 0, t is less than a equals to 1 if t is greater than or equal to a, where the quantity t minus a is called argument of the function. Another shifted unit step function which remains at 0 value as long as t plus a, the argument is less than 0, the function abruptly changes to unity value at t equals to minus a. That function, you can represent this t, amplitude here 1 as it is unity, minus a, this is minus t. Then this function can be expressed as u of t plus a equals to 0 for t is less than minus a, equal to 1 if t is greater than or equal to minus a. So at minus a, the signal abruptly changes to unity. Similarly, two other functions of shifted unit step function are, let it be a, and it is expressed as u of a minus t equals to 0 for t is greater than a and equals to 1 for t is less than or equal to a. So at a, it abruptly changes to 1. The argument is negative. And another shifted unit step function is t, is amplitude 1, 0, minus a, minus t. The value changes from 0 to 1 at t equals to minus a. And this can be expressed u of minus a minus t, which equals to 0 for t is greater than minus a, 1 for t is less than or equal to minus a. Next one, ramp function. When a time variant current or voltage increases linearly with the time, it is known as ramp function or simply ordinary ramp. Shown like this, with respect to time, amplitude need to change like this. Now consider unit step voltage applied to an inductor as shown. Now the current IL is given by 1 by L integral minus infinity to t Vs dt. As Vs is the unit step input, Vs equals to 1. Assuming the 0 initial condition that IL at 0 not equals to 0, then IL equals to, we are going to get t by L. This response current constitutes the ramp function where the inductor current is seen to vary linearly with respect to time. This is t and this is IL. 1 by L is constant, and as t increases, IL increases. Similarly, unit step current IC is applied through a capacitor C. Then the voltage across the capacitor Vc is given by 1 by C integral IC of dt. As this is a step input of the current equals to 1 and the initial conditions equals to 0, then Vc is given by t by C. This also going to increase with respect to time, Vc as a ramp function. Thus, the response of unit step function of the voltage to the inductor and of the current to the capacitor gives us the ramp function of response, that is the inductor current and capacitor voltage. Now, it can be said that the integration of the step function results in the ramp function R of t. Now, impulse function, which is represented like this. When a current IL flows through an inductor, the voltage induced is given by VL equals to L into dIL by dt, and this VL is directed to oppose the IL. And assume IL equals to unit step function u of t, then dIL by dt equals to 0. Thus, a derivative dIL by dt is 0 for all time except t equals to 0. That is, at the moment when stepping occurs at t equals to 0, the slope would become infinity. Then dIL by dt will become infinity at 0 t. Thus, the response of the step current at inductor makes an impulse. As is shown here, at t equals to 0, this will reach maximum peak of infinity and comes back to 0 at 0 plus. That is, the function is infinity at t equals to 0 and 0 at t is greater than 0. Similarly, the application of unit step voltage to a capacitor is IC is given by C dVc by dt. So, if Vc equals to unit step voltage, then dVc by dt equals to 0 at the time t equals to 0, dVc by dt equals to infinity. When t is greater than 0, this value will become equals to 0. And similarly, here also when t is greater than 0, this value will become equals to 0. From this, we can say that the differentiation of the step function results in impulse function. So d by dt of u of t equals to the impulse function delta t. An unit impulse function is denoted by delta t minus t1, where t1 is the instant of the time at which the pulse occurs. Obviously, if the pulse occurs at the origin, then t1 will become 0, leading to the unit impulse function to be delta t. In our case, it is 0. Further, as the differentiation of step function results in impulse function, hence we can say that the integration of unit impulse function would result in unit step function. Next function, unit doublet function. And the graph which represents unit doublet function, that is t to infinity minus infinity at t equals to 0, differentiating unit impulse function, that is d by dt of delta t minus t1 equals to 0 equals to minus infinity for t is not equals to t1, for t equals to t1 and minus infinity. The function d by dt of delta t minus t1 is called unit doublet function. It may be noted that starting from the unit step function, successive integration results in new functions. This is our step function. If you integrate this function, you are going to get a ramp function. Again, if you integrate the ramp function, you are going to get unit parabolic function, this is t square by 2. And again, if you integrate this function, we'll be getting unit cubic function. This is t cube by 6. Now, similarly, for the step input t, if you differentiate with respect to time, we know that you are going to get an impulse function. Again, if you differentiate this function with respect to time, then you are going to get unit doublet function. The differentiation of step function gives us unit impulse function, which on further differentiation gives us unit doublet function. This is regarding the basic types of special signals. If this video is useful, please like, share and subscribe.